All right, everybody. So today we are doing an introduction to limits. Limits is traditionally the last topic covered in a pre-calculus curriculum, and limits are traditionally the first topic covered in a calculus curriculum. So that's sort of the bridge connecting you from the pre-calculus to the actual calculus. Limits, if you have a really good um, unit on limits when you're in a pre-calculus course, it does make calculus way easier, and you can kind of get into special, more intriguing limits sooner than later. So we are going to just be doing a big introduction right now, and we're building in our algebra and our geometry review. So calculus is the place where all of the math you have ever really learned ever, everything from when you were young, straight through algebra, geometry, algebra 2, pre-calculus, it just is like, this is why you needed to know all of it. Hope you remember everything. Hope you didn't forget. So you really, really, really want to work on figuring out what technique works best for you to ensure that the things that we're going over are not just things that you memorized for one day, not just things that you knew for a unit, a quiz, a chapter, a week, or a month, that they are a part of you now, okay? They're a part of everything. They should be very natural to you, and that you should just be able to think about it, talk about it, write about it without any struggle. So but definitely like let me know which things you need more practice with, which things you really don't understand or can't wrap your mind around, and we will work on making it better. So limits. First thing we have here is we're going to have our definition, okay? Now, like most definitions in math, we can write out a definition using notation, or this is notation form right over here in this box, or we can use more with words. So these are two different descriptions. You're going to notice if you reference a calculus textbook especially, and if your teacher does show you both, you're going to notice that there's often two definitions or two descriptions for almost everything in calculus. I just tend to notice like some textbooks have one, another textbook will have the other, and some textbooks will have both. But it always seems to me that there is like style number one and style number two. So when we start talking about things like continuity, when we start talking about things like differentiability, or maybe next year when you do that, you're going to have two different descriptions. And I would definitely write them both down, read them both to yourself, and make sure you understand that they both mean the same thing. They're expressing it with different words, and kind of try to figure out which one is best for you. Okay. So over here, I'm going to go and read you this notation form first. Notation form, you want to make sure you read it the correct way. When you're not listening and you only watch and write things down, you tend to call things by the wrong name. You might pronounce it wrong. So make sure you're really tuned in. This can be read, and there's also two ways, I guess, that you could read this, but you could read this as the limit as x approaches c of f of x is n. So to say that again, the limit as x approaches c of f of x is n, or we could kind of swap this order, and we could say the limit of f of x as x approaches c is n. They mean the same thing. You definitely need to indicate what you're approaching, because your limit, sort of like in algebra when you had your independent variable x and your dependent variable y, your output or your range or your dependent solution, it depended on which x value you were plugging in. So limits are very, very similar in that way, where the answer to your limit, in this case, the answer is something we are calling n right now. Your answer depends on what number you're approaching. if you're approaching 5, if you're approaching 2, if you're approaching 0. It all will impact what your actual limit is. Also, which function you're using. F of x could be x squared. F of x could be square root of x. F of x could be 1 over x, or any combination or transformation of any of those things. So what function is it? What are you approaching? And your result depends on that. All right. After we have this notation form, we have it written with a description to explain what it all means, really. All right. And I would suggest, if you're the type of person who wants to take AP Calc one day and do really well, or wants to make sure that you do well in college calculus, I would revisit definitions and reread them to myself if I were you, as you get better at doing the examples. Because the words, just like if you were a lawyer, the words that are in the law, you got to really make sure you're following that language. You want to look for a loophole, look for a little snag or something that you could get caught up on or misinterpret, and you want to make sure that you are following it to a T. Description 1, for all x approximately equal to c. So x is approaching 5. What number is a number? Give me an example of something approximately equal to 5. What number is approximately equal to 5? 4.9, 4.99, 4.99999. I probably wouldn't use 4. I mean, even 4.9 has an infinite number of numbers between that and 5, but we get as close as we can without sounding like a maniac. Or you could even go on the other side. That was on the left of 5. What about on the right? On the right of 5, 5.01. 5.0001, right? So we have all these numbers. So for all x approximately equal to c. Okay, got it. Stage 1. With x not equal to c. So it's approximately equal, not actually equal. So we're not worried about it actually being 5, just numbers really close to 5. The corresponding value of f of x is approximately equal to n. Now that part's a little bit harder to grasp, but if you have a function and we want to know the limit, you really want to know what y value, so just like we're getting really close to this x with the 4.9s and the 5.1s, we could get really close to the x value. We want to know, well, all right, as my x's get closer and closer from both sides, we're like, okay, coming closer, 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 closer. If you had a sibling, if they ever played that thing like, I'm not touching you, I'm not touching you, and they have their hand in your face and they're just being annoying. So, x is like, I'm not touching you, I'm not touching you. It's getting closer and closer and closer on both sides. Now we want to look at the y values. What about this way? Are we closing in on a y value? If we are, which y value is it? That y value is n. That's your limit. That's what you're approaching. If we're approaching one number on the left and another number on the right, we're not approaching a number, the limit won't exist. All right? But we'll get more into that later. So that's the one description, and here's the other. It's the same description, just done a little differently. This one says, as x gets closer to c, but remains unequal to c, the corresponding value of f of x. Remember that f of x, when they say the value of f of x, that's your output. That's what they mean. Okay? They don't go into all that wording. They're not going to say the output, the y value. You need to know that when something says f of x, that implies an output or a y value after you plugged in an x value, an output y value, okay? Gets closer to n. So the word closer is in both of these definitions, or approximately, and that's really important. So you need to remember, we do not need to ever actually reach that x value or reach that y value. There could be a big gaping hole in your paper, stabbed right through your paper. You could hold it up, look through it, but it still wants to know, what are you closing in on? All right, what are you getting closer and closer to? So hopefully we all wrote that down, and we're going to go into some baby examples at first. I'm going to be real extra as I go through these baby examples, but the reason I'm doing that, think of that as an English class, like foreshadowing, right? Like, I know what's coming. I know where you're going to get tripped up in a future example, so I'm going to talk about it on something easy, introductory now on these examples, okay? Example number 1. Find the limit as x approaches 3 of 5x squared. So this one, baby example, very easy. Has great characteristics, things that we love about it. So first, I'm going to explain this example graphically, okay? Now, 5x squared is the function, all right? You don't necessarily need to write all this stuff down. I'm just going way into it, okay? My function that I'm finding the limit of f of x is 5x squared. That is a transformed version of the parent function y equals x squared, which is a quadratic. Y equals x squared, you really want to just know what that graph is by heart. The name of that type of function is a quadratic function, and the graph is known as a parabola. And I'm just going to throw some tick marks over here. We did review this earlier, but baby review of the parent. The vertex is at the origin, 0, 0. Anytime you describe where something is, it's a point, it's an ordered pair. You should describe both x and y. Pet peeve is when students try to tell me that I need to put something at the origin and they tell me to put it at 0. That's just the one number. I need two numbers. I need x and I need y. All right. So 0, 0, origin. The origin is where we originate for our graph. Now, x squared, the parent, I'm going to go out 1 and up 1 because 1 squared and negative 1 squared are both 1. Then I'm going to go out 1, my trick. I'm only going to go up 3 this time. 1, 2, 3. I was already up 1. I went up 3 more, and now I'm up 4. Why is this good? It makes sense because 2 squared and negative 2 squared are both 4. If I needed one more point, I would need to go out 1, and I'm going to go up 5, up 7, up 9, and continue with the odds. So up 1, 2, 3, 4, and 5. Out 1 and 1, 2, 3, 4, and 5. I think it's easier to pick up where I left off when I'm plotting points. And I was already up 4. I went up 5 more. I'm up 9 now. Why is that good? Because 3 and negative 3 squared are 9. All right. This lovely graph over here is the parent function, y equals x squared. Some vocab for you that's going to be super relevant when you get to just maybe a couple months into calculus. You are going to do things known as the first derivative test and the second derivative test. And the first derivative test will tell you where a graph, without knowing what that graph is, like something that doesn't really have a parent function, where is that graph increasing from left to right? Where is that graph decreasing from left to right? Where is that graph changing direction? So here I would say, I'm going to trace over, I would say the graph is decreasing, just some vocab, from negative infinity, because I'm describing it from left to right, decreasing from negative infinity until 0. I would describe that with a parenthesis on the 0. Then I would say this graph is increasing from 0 until infinity, because if you go this way, your graph is increasing. You need to remember that your graphs, anything with the graphs, is described from left to right except the range. Everything left to right, left to right, left to right. Domain, continuity, increasing, decreasing. Where is it concave up? Where is it concave down? Any interval that you're describing will be as domain, intervals of the domain, and you describe from left to right. The only one you don't is if you're asked for range, and that goes from the bottom to the top. So just to kind of throw those over here. Increasing, I would describe as negative infinity until 0. Decreasing, I would describe as from 0 to positive infinity, left to right. I would say, so here's a couple of things. Again, it's all for getting ready for calc. If you have, did I write the wrong thing though? I wrote it backwards. I wrote it backwards and you didn't stop me. So let's switch that. Decreasing and then it's increasing, yeah? Yeah. So if you, in calculus, what a derivative will do for you, and you need to learn limits in order to learn derivatives, because we use a limit to create a derivative. Like it really is like what came first, the chicken or the egg? No paradox. You need a limit to come up with a derivative. So that's why we learn them first. Now, a derivative, what that does for us though, is it allows us to determine the slope or rate of change of anything. As of right now, the only things that you guys are finding a slope of would be like a line, something that you have a constant slope. Your slope is always 5/3, up 5/3, up 5/3, up 5/3, flat line. Cool. Okay, that's if your slope never changes. But look here, we have a curve. When you have a curve, your slope is just changing all the time. And guess what? Your slope, like a lot of things, depends on x. So here I have a very steep slope. What we do is to figure out the slope, it's actually of a tangent line. So we're going to go like that and kind of hold a line to it. So when I'm decreasing, what kind of slope do you have? Well, negative. Then here, when you're increasing, what kind of slope do we have? Again, from left to right, positive. So we use parentheses for these intervals. What do you think we could say is true about the slope right there at 0 when x equals 0? What do you think is true about the slope of this curve at 0? When it's decreasing, we have a negative slope. When it's increasing, we have a positive slope. What do you think the slope is here at 0?
0.
It's 0. So that's a negative slope. These are all like gems for your future. Positive slope. And then the slope when x equals 0 is 0. And if you think about this, you guys remember the word we use to describe something that you can draw without picking up your pen or your pencil? There was a C word to describe something that you could draw as a graph without ever picking up your pen or your pencil.
Continuous.
Nice. So these are continuous, either one. In fact, a good rule is all polynomials, because this qualifies as a polynomial, all polynomials are continuous. So if you have a continuous set of numbers, how do you get from negatives to positives without passing 0? It's impossible. In order to go from negatives to positives, you're going to pass through 0 if a graph is continuous. It is possible, if you think about the volcano, and we'll talk about it later, you have a positive slope, then you have a negative slope. You don't have a slope of 0 in between, but it's not continuous. We're magically jumping over a vertical asymptote, okay? So all of this stuff is going to play a huge role later. But the fact that polynomials are continuous make limits a breeze. One other thing though, I'm going to describe that this graph is concavity, concave up. You could describe something as concave up or concave down. Concave up from negative infinity to infinity. It's always concave up. Concave up looks like a cup. It even looks like the U in the word up. So it's curved that way. Concave down looks like a frown. It's going to be curved the other way. And we'll get more into that later as well. First derivative in calc, you're going to talk about a lot of stuff here. Second derivative will relate to this stuff over there. Anyhow, we want to find the limit as x is approaching 3. If we compare this to the definition, let's look at this one. As x gets closer to c, in this case, what's c? 3. As x gets closer to 3, but remains unequal to 3. We're just getting closer to 3 for the x value. The corresponding value of the function, the y value, gets closer to our limit. In an ideal world, that is. So if I try to close in, what can I use for this? Let's use markers. Here's 3. I don't have the whole graph drawn for this, but if this is 3, this is still the parent function. I didn't draw the real one. You're going to kind of close in from left and right on 3 and try to figure out, are you closing in on a y value? And if you are, boom, that's your answer. So if I were to sketch this, the 5 will create a vertical stretch. Now, a stretch of 5, that's pretty steep, and I'm not going to really be able to fit this on my paper to scale. Go over 1, up 1 is now going over 1 and up 5, vertical stretch of 5. So 2, 3, 4, and 5, and 5. I don't even want to do the second point. Over 1 up 3 will be over 3 up 15. Over 1 and up 5 is now going to be over 1 and up 25. No thank you. That's a little bit too steep. You're not going to have a graph all the time, but if you could hold one in your head, that'll be good. If you know that this is continuous, you have an idea of what the shape looks like. The fact that you know it's a polynomial and that all polynomials are continuous, that means there's really no mystery to what the y value will be. As we get closer and closer, as we get from both sides to the x value of 3, what do you think the cheapest, easiest way to get the limit answer would be in a case like this where you have a polynomial, it's continuous, nice smooth graph, don't have any issues drawing it, no holes in it, no asymptotes in it, no piecewise functions that have a jump? What do you think the easiest, cheapest way is to getting my limit, which is the y value we're closing in on? Anyone have a suggestion? It's pretty.
Could you just plug in 3 for x?
That's it. That's called direct substitution. Are they all this easy? No freaking way. But in the beginning, yeah, you'll do a bunch of these. Are we going to do a bunch of these? No, but we'll do a couple here and there sporadically. So this is the question. That's the operation you're applying, is taking the limit, like a square root, like sine. You stop writing it once you take the limit. So if I'm doing direct sub, 5, 3 squared, I don't write limit this step, okay? You don't write it because you're taking it. Then 3 squared, please, guys, PEMDAS, don't be that person. Don't multiply 5 and 3 first. 3 squared is 9, and 5 times 9 is 45. So that is your limit. The limit is 45, okay? We're done. It's continuous. It makes sense because we should know it's up pretty high. I know I have a steep graph. I don't necessarily have to graph the whole thing. And that is just the end of it there. All right. So we're going to do another example now. Any question on example 1? Wrote down your definitions, your vocab. We're good, right? All right. Next, example 2. Do you guys remember what a rational function is? What a rational function is, whether maybe you remember what the equation would look like. Maybe you remember what the graph would look like. Rational, or what does rational make you think of? Ratio? What's a ratio in math? Ratio or rational is a fraction. Ratio 2 to 3, 2/3, right? So in example 2, we're going to find the limit as x approaches 2 of this rational function. We have a fraction where the top is the polynomial and the bottom is a polynomial. That is a formula, magic formula for a rational function. So polynomial, poly means many, nomial means terms. Polynomial, in fact, it's a quadratic binomial on top and a linear binomial on bottom. And that created this rational function for us. Now, will direct sub work on this example? Why or why not? Will direct substitution work here? We just plug it in and be like, done. Got an answer, got a number.
Wouldn't that only give you one of 2 answers then?
Not that it would even give you one of 2. What would happen if you plugged in 2?
You get, you have to divide by 0, which doesn't work.
Which doesn't. Just stop right there. Perfect. Which doesn't. Okay. We can't divide by 0. So things you need to remember. Use 1 as the example. 1 over 0. 0 over 1. This is part of our big algebra review here. 1 over 0, if you see 1 over 0 in your work and you're like, oh, 1 over 0, you're going to say to yourself, no. What does no mean? Undefined. That's what no means. And does it have to be a 1? No, it could be any number. I just use 1 because it's easier to turn it into no. So a number over 0. If you have a 0 over 1 or a number, that's okay. That equals 0. 0 on top of a number, that's okay. However, if you get 0 over 0, does anybody know anything about that? 0 over 0. What the heck is 0 over 0?
0.
Not 0. 0 over another number is 0. I'm sorry,
Still
yeah.
undefined.
And it's not undefined. It's neither of those things. This is something we can call indeterminate form. A-T-E or A-N-T? Can one of you check the spelling? Indeterminate form. Indeterminate form. And think that it looks like, if I'm wrong, let me know, a division symbol. I don't know if you guys can hear my dog whimpering in the background. I hope that the noise canceling is like not letting you have to hear it. But he knows it's nice outside and he just wants to lay on the sidewalk and he's crying by the door. So if you hear him, I'm sorry. He just lays down on the sidewalk in the sun and won't even walk and like doesn't want to come in. So this is indeterminate form, and I want you to think how it looks like a division symbol. Can you guys see that? Like 2 dots over with the line in between, right? When it looks like a division symbol, think of this as a big hint that you can divide something out. 1, 2, and 3 are one of the main reasons that students doing limits and calculus get points off, get questions wrong. These 3 things right here. Put it in your brain, write it down. I would not have taken the time to write down this ridiculous little thing here if it wasn't really important. If it wasn't something that I constantly had to take points off for students. Okay? Get that down. So let's see what happens if we try direct substitution like we just did. Try direct sub. We would get 2 squared minus 4. Obviously, this is a little bit more obvious and you could see the answer a little quicker and do it in your head. But, you know, humor me because they're not all this easy. All over 2 minus 2. You cannot reduce the 2's. You cannot reduce the x's. If you did that, smack your hand and say very bad and never do that again. You cannot reduce the x squared and the x. You cannot reduce the 4 and the 2. No one ever showed you that. You made that up. No one ever showed you that. You are never allowed to cross something out that is separated with addition and subtraction, no matter how tempting it looks, okay? 2 squared is 4 minus 4. The bottom is just 0, right? And then that gives us, boom, 0 over 0. Almost everything we do with limits in calculus ends up being 0 over 0. And that means you just got to do some work. You're going to fix it, and then you're going to find the limit after you fix it, okay? Do you guys know what spackle is, or DAP? Spackle, DAP, yeah. Just a hand raise button if you do know what it is. 1 person, so I'm assuming no one knows. So spackle is that stuff that you put the putty with the little flat spatula knife when you have a hole in the wall, bloop, and you go, here you go, and you sand it a little bit when it dries, and you paint over it, and it's like you never had a hole in the wall, okay? Now, this graph over here, When you end up getting 0 over 0, that means you have a hole in your graph. And in order to find the limit, we want to put some spackle in that hole. We're just going to be like, bloop, let's fill up that hole. But we also need to know what the graph looks like to know where the hole, what kind of graph has a hole in it, right? So how do you handle something like this? This is part of our super duper algebra review. If I were trying to graph y equals x squared minus 4 over x minus 2, you nearly always need to factor. Just remember that. Like, when in doubt, factor. When in doubt, graph it out. That's super. But also factor, okay? It doesn't rhyme, but just do it. So I really hope that we all know how to factor this numerator. Fingers crossed. Everyone knows how to factor this numerator? Anybody want to tell me what it is? Come on. How about maybe, let's see, go down this line. Makai, Nolan, James, Catherine, George, Alex R, or Bela. How do I factor that numerator? No one? No one?
X plus 2, x minus 2.
There we go. Thank you. Difference of squares, x plus 2 and x minus 2. So they are conjugates because when you FOIL, outer and inner cancel out and you just get x squared minus 4. Amazing. Now, not only, think of the spackle, okay? Not only does the spackle, bloop, fill in the hole for you when you have a hole in the wall, but, he gave up by the door, he's next to me now. But the spackle, you could also think of the motion of spackling. That, the fact that you have an x minus 2 on top and bottom as a factor on top and on bottom, when you go bloop, cross it out, you're spackling and you're filling in a hole in your graph. What graph? Whatever is left after you cross out and spackle those holes, whatever is left behind, because you got more than one hole, is the thing that your graph will look like. What's left behind is just y equals x plus 2. What is y equals x plus 2 going to be when you graph it? Y equals x plus 2. Come on, one of the first things you ever graph. Don't be a weenie. Participate.
It's gonna be linear.
Yeah, it's a line. It's slope-intercept form of a line. The slope is 1. The y-intercept, the intercept is positive 2. And we just draw a cute little line. All right, so I'm going to do that. I'm going to put a little extra room around this. So x plus 2, 1, 2, 1, 2, 3, 4. 2, 3, 4. So I went up as high as 6, down 4, left 4, right 4. Okay. X-axis and y-axis. All right. So if I'm going to graph this cutie patootie over here, let me grab my letter here. So I'm just graphing what's left behind. What's left behind is x plus 2. I go up 1, 2, y-intercept. If you do not know how to graph a line, some of you don't, and you think you do because you've messed up on things. So don't be too confident. Please be paying attention. Some of you don't know how to graph lines. There's 2. The slope is 1. That's 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1 from there, and then -1, -1, still positive 1, down and left, yada, yada. Okay, so that would be my line. But we spackled a hole. Where was this rational function undefined? Where was, before we spackled, where was this rational function undefined? At which x value?
2.
Good. 2. Usually, 90% of the time, the number that they ask you to approach in the limit, they pick the annoying number. That's what they do. Pick the worst case. Because obviously, if you could direct sub for 1, you could direct sub for everything that's direct subbable. I don't think there's going to be an issue. Where's the issue going to reside? In anything that you can't use direct sub on. So of course, they're always going to ask you in a limit question, once you do a couple direct sub, to approach any number that will cause the denominator to equal 0. Sometimes the numerator will also equal 0. Sometimes just the bottom, and you have to do each case as it comes. So it's undefined at x equals positive 2, because if you fill in a positive 2 for x, 2 minus 2 on bottom gives you 0. It is not undefined at negative 2. I know it says x minus 2. Don't be that person. That's silly. Negative 2 is fine. It doesn't give you a 0 on bottom. Okay, pay attention. So at 2, what you'll do before you draw your graph is you're going to find where x equals 2. Don't get confused because we've got a lot of 2's. And we're going to go up to our graph and we're going to draw a big open circle. That big open circle is a hole. H-O-L-E. Your graph has a hole in it. Just like when you have hole punch paper, your paper's got a hole in it. You write there, it falls into the abyss. It won't be on the paper when you turn it in, right? The rest of the line is fine. So visually, I have a line that looks a lot like the line y equals x plus 2. However, I drew a ginormous hole. That hole is not really that ginormous. It is microscopic. It's teeny, teeny nothing, right? It's only when x equals 2. It's not at 2.1. It's not at 2.01. It's not at 1.9 repeating. It is literally only at 2. So why do I draw that big circle? Because we're humans and our eyeballs can't see things that are microscopic. So we draw a big doofy circle so that we don't forget that we have a hole in our graph, okay? Now, when we spackled, what happened was we filled in the hole. So now we're good. So this is this, but with the hole filled in. What does that mean? If I want to find the limit of this, I could find the limit of this. And I get the same answer. Because nowhere in the definition of a limit does it say you have to get to that number, right? They just want you to get really close to it. So are you getting really close to a singular y value? Yeah. Which y value? The one that the hole's at. Okay? Now, how do you show your work properly for this? You need to write limit every step of the way until you find that limit. So I'm going to show you how you would write your work for full credit, most especially if you're going to take a college calc. Believe me, it's right or it's wrong. And if you don't write limit every step of the way in your college math class for a limit problem, they're not even going to read it and humor you. They're going to mark it wrong. It's wrong. You called it the wrong thing. You're wrong. You need to know when to write it and when to not write it. So I'm just going to start clean here. The limit as x, so if you have room on your paper the way it is, then you just go from there. As x approaches 2 of, now maybe you want to put a parenthesis around it, whatever, x squared minus 4 over x minus 2. I tend to try to do my work vertically, and when I do it vertically, I don't write an equal sign every step of the way. There was no equal sign. But if I go horizontally, I might use an equal sign, sometimes an arrow pointing to the right to kind of show where I'm going. So I'm going to go underneath it. That's the same as, next step, x plus 2, x minus 2 over x minus 2. There's implied parentheses around the bottom. Next step, we're going to simplify or reduce. That's us spackling the hole, getting rid of the problem. And that leaves us with the limit as x approaches 2 of x plus 2. The limit of that are equal. Are they equal just like this? No, they're not the same, but their limits are the same. They have the same limit. You're going to approach the same y value for both of them. Now in the next step, 2 plus 2, that's me doing direct sub. I'm now taking the limit, and if I'm taking the limit, I don't write limit anymore, and then that answer is 4. So what else could I write as like a full statement? You might write the limit as x approaches 2 of x squared minus 4 over x minus 2 is 4. All right, And that would be your answer. Okay. Graphically, your graph should support that. Do you always have to graph it? No. There is another way where people teach you to find limits using a table. I think it's the dumbest thing ever. We no longer live in caves and use like stone tablets. And I'm not going to even waste my time showing that to you. If your teacher shows it to you next year, go nuts. But I think it's ridiculous that we do that. I think I could explain that graphically what they would show in a table. So I'm skipping that. And if you look here, there's 4. The ordered pair of the whole, okay, it's a whole, I'm labeling it, is at 2, 4. That's why the limit as x approaches 2 is 4. Does anybody remember the other word or phrase actually to describe a whole, the more proper phrase for that type of, I'm going to give it away. Wholes are also known as, you think you know, Bela? Or
Are they asymptotes?
not asymptotes, those are going to be the dotted lines. So an asymptote is what we call an infinite discontinuity. Because it's a whole, it's not an infinite discontinuity, it is a something else discontinuity. There's infinite, then there's
Finite.
It's not finite, that wouldn't be the word. There's an R word. An R word for a type and a J word. I always spell this wrong. I don't know if I dropped the E or not. Correct me if I spelled it incorrectly. Don't let me keep it in the video run. Did anyone check my spelling on that other word before? Indeterminate. Did anyone check it? No one, no one. Thanks, guys. You could just type it in the chat. See if it comes up as a spell check. I'll do it. Don't worry, guys. Don't stop what you're doing. It's fine. I think that's right. Yes, I think that's right. And now remove bubble. Nope. I think you take the E out. Yup. No E in removable. We remove the E. Come on. Silly me. Don't let me make that mistake again if I forget in like a day. I don't know why this does not stick in my head. I've been doing this for years. I'm dumb with it. So these are also known as removable. Bela brought up asymptotes. Vertical asymptotes are infinite discontinuities. Chris mentioned the word finite. So that's an interesting thought process, and that's a good one because usually we classify a discontinuity. So here's more of our algebra review. Also, if a graph has a discontinuity, it's not continuous. If it's not continuous, that means in order to draw it, you have to pick up your pen or your pencil technically. So it's not a continuous function. It is discontinuous. And there are 3 types of discontinuities that we talk about, and we could kind of put them into 2 categories. So you have the removable discontinuities. And we have non-removable. So kind of like how you said finite, that was like pretty good line of thought. Non-removable discontinuities. The removable discontinuities are things like wholes. Okay, non-removable discontinuities, we have 2 types that we're going to think of. The one, like Bela mentioned, the vertical asymptotes. Vertical, not CLE. All right, last thing we were doing, okay? Asymptotes. And those are infinite discontinuities. I'm just going to abbreviate there. And then, does anybody remember the other type? It starts with a J. It's in like when you guys did piecewise functions. They're called jump discontinuities. So they were either in something like a piecewise function, maybe you had something that looked like that, and then you had something that looked like that, right? That was a jump discontinuity. All right. Vertical asymptotes are your jump discontinuities. I don't know why I kind of, whatever. There we go. So that's what they look like graphically. And I could draw, say, like the volcano. Like there. And then the holes we just saw, it could be in anything. You could have a hole in a parabola. We could have a hole in a line. You could have a hole in a cubing function. You could have two holes, whatever. Okay, so that's what a hole would look like. They're removable because you could spackle them in your equation. Non-removable, you can't spackle it, okay? Cannot get rid of it. All right, that's the end of that. So we will start. I will probably continue this recording elsewhere, but I will also do the limit. I'm going to flip this upside down, okay? As x approaches 2 of, that'll be example 3, x minus 2 over x squared minus 4. So you may want to get a head start and try that out. Keep going with your checking and correcting, and I will share the honors examples. And if I can get to recording continued part of this, I will. And otherwise, you can have a great day. If you understood what we talked about today, thumbs up. Anything that you would need more explanation of, if you're watching this on YouTube, please just make a list for me on the bottom. Like, I'm horrible at these things. Can we talk about them in more detail? Let me know, okay? Adios.
Ms.